Hello everyone. This is my presentation for the final project that I did in pattern recognition course here at University of Florida. The topic for today's presentation is optical character recognition using classification techniques. So let's move on to the problem statement. Optical character recognition. Optical character recognition is the process of recognizing and extracting characters and other textual information from images. Whenever we take a photograph, uh, the image contains a lot of text, but uh, we can't extract any meaningful information out of it apart from using that image for storage purposes. Now, with optical character recognition or OCR, we can extract the text which is present in these images, and we can use that information in any other format as necessary. Uh, So the recognized text will be in a machine-friendly format, and the images which I'm talking about right now, these are the input images, and these input images can contain text which is either handwritten, typed, or any other font, and OCR aims to recognize these texts from these texts. Okay. There are many real-world use cases with respect to OCR. I've listed some of them right here. So the first one is automatic number plate recognition. So this is a system which can be very helpful in settings such as toll plazas, where uh, any auto or any other vehicle can just drive through the toll plaza, and the number plate is recognized automatically, and the toll charges are billed to the respective drivers. So this mechanism can speed up the toll process, and can also help in reduction of traffic. Another similar application would be monitoring the traffic via cameras at every signal. So the second application which we can talk about is simplifying document storage and retrieval. So any image, or precisely any high quality image, can range from 1 MB to uh, several hundreds of MBs. But if we only are storing these images because we need the text within which is present in these images, it would be much more efficient to extract the text part of that image and store it in a much smaller space. So that for simplifying these document storages and retrieval. So when we talk about retrieval, we can also implement search and any other text capabilities on top of these documents which was not available beforehand. So the third application would be digitization of ancient texts, where a lot of ancient scriptures and other texts which were written across the last uh, century, or maybe during the BC time. All these uh, all these ancient texts are handwritten, it, and it would be very hard to find duplicate copies for these texts. By using OCR, we can scan the images of these scriptures, and extract the text information out of it and store it and make that information easily available online. That way we can help immortalize any of these ancient scriptures, the and the data would stay on the internet forever. So the fourth application would be browser plugins. This is a recent entry into the OCR field, and one major example would be Project Naphtha. Project Naphtha is a browser plugin which can help the user in easily copy pasting text from images as if it was any other regular text field. Uh, this plugin does this feature with such a simplicity and such a simplicity that the user will have enhanced experience and uh, and can extract text out of images, which was not possible previously. So moving on to the process. So the OCR process can be categorized into many phases. The each uh, There are 5 to 6 phases which are mentioned here. The first phase would be data collection, or the input images collection, where the images from which the text has to be extracted are gathered. Those images are sent to pre-processing phase, which is then sent to segmentation, feature extraction, and finally the classification phase, from which the output text is extracted. In each phase, the images undergoes a set of transformations and removes unnecessary information and prepares this particular image for the next phase to be operated upon. So the end result of this OCR process would be machine readable text. So as you can see, the OCR of process is described in this diagram below. We take on the input images and we pre-process them, and the pre-processed image would be sent to the segmentation phase. After the segmentation, we send it to feature extraction phase, where we extract useful features out of the segmented images. These features are sent into the classification phase, where classifiers identify the key features and map most of the input characters onto the real world characters, and from which the output text can be generated. So gathering input images. Input images are majorly categorized into two categories. So handwritten text and typed text. So typed text is the most popular format, and it can be seen everywhere, from screenshots to photos to number plates to about anything else. We find it on the internet. Handwritten text images are a little bit more complicated. So the most frequent way of obtaining these images is by taking photos or scanning the physical copies or of these handwritten documents. And performing OCR application is relatively harder on these documents as compared to the typed text, because of the varying fonts and varying styles of handwritings. So, here you can see a test image. It just says test message in a typed format. Now, if I now we talk about the pre-processing phase. So, pre-processing phase is the phase where we remove unnecessary information and just prepare the image for a text identification. Specifically, in this pre-processing phase, we try to remove the noise which is present in the image, and we try to highlight the textual part of it. The noise can be removed by using Gaussian blur and median blur. Go- Median blur is the process in which you, for every pixel, you set the intensity to the median of a particular range around that pixel, and Gaussian blur is obtained by performing a Gaussian operation on the image. The end result of by performing these blurs is the image is smoothened out, and there are not much of noise present in the image. Once the image is smoothed out, it is sent through adaptive thresholding to highlight the textual content. Adaptive thresholding is a kind of image thresholding, where the threshold value is determined by the local neighborhood of any given pixel. So after the thresholding is done, irrespective of the illumination levels of each of the the image uh, image contains only the main idea is that after the adaptive thresholding is done, the text part of the image should be much more highlighted as compared to its neighborhood, and uh, we can see here in the next image that the edges are a little bit blurred, and uh, it is a little bit more crisp, little bit more highlighted as compared to the previous input image. Now we can move on to the segmentation phase, where we try to identify the actual textual regions in the image. So in this process, we are trying to identify the text blobs which are present in it, and we use a technique called dilation, which is done via the MSCR algorithms, which MSCR stands for maximally stable extremal regions. And MSCR algorithms, we do have an OpenCV implementation for that, and we are using this implementation in our project to highlight the textual regions. So after we apply the dilation, the image, then the end result would be that we would get image which shows the blobs of text or blobs of probable textual areas within the image. So the idea is that these blobs represent words, and to actually get the individual character regions, we have to apply dilation again within these uh, textual blobs. So it is a two-level process, for one for words and other for characters. And we tend to draw bounding rectangles on each of the blobs detected, and these bounding rectangles uh, are what is used in future phases. For example, in this, once we identify a character in the textual area, we draw a bounding rectangle onto it, and the portion of the image represented by this bounding rectangle is sent into feature selection and classification phase, where we try to determine whether this particular bounding rectangle represents any of the 26 letter alphabet. So here in this image you can see that at the top level there are two bounding rectangles, one around test and the other around message. Within each bounding rectangle you can see that there are multiple bounding rectangles each around the character. So one thing to notice is that we need to finalize on an order in which the extracted words can be represented. So the current order which we are choosing right now is the most frequently used, top to bottom and left to right, which is in consistency with the English alphabet. So words whose x and y values match in this particular order are sorted, and I mean the bounding rectangles are sorted in this particular order, and the output text is actually uh, shows the words detected in these regions. So currently there is a variance of 10% included in our programs, because there are many scenarios where the bounding rectangles are not are not exactly in the same line, even though they appear to be in the same line. Their x coordinates and y coordinates vary, and by including a variance like this, we can make sure that all the y coordinates within a 10% range uh, are part of the same line. So this variance can be changed based on individual use cases, but the underlying concept remains the same. So we now move on to the feature selection and extraction phase. The feature selection and the extraction phase is where we extract useful features. So the most probable features here are average x coordinate, average y coordinate, black aligned count, and grid vector. Average x coordinate. The mean for a given bounding rectangle, the the mean x coordinate for all the white pixels is just the average x coordinate. Average y coordinate again is the same logic for the mean y coordinate for every white pixel present in the bounding rectangle. Black islands. Black islands are the continuous regions where every pixel is black. Uh, in this particular images given below, the image B has 5 black islands and image C has 4 black islands. So we now move on to another feature known as grid vector. Grid vector is the concept of splitting a bounding rectangle into a particular k cross k grid. Now, based on the information present in this bounding rectangle, we try to assign a value of 0 or 1 to each grid cell. A grid cell is assigned a value of 1 if there is at least one white pixel in the cell. So here, as we can see, in this 4 by 4 grid vector, wherever there is information related to the letter T, we have represented the cell with a value of 1. Once the features are extracted, we move on to the classification phase. Uh, Classification maps the input feature vector to one of the output classes. The output classes here are characters A to Z and digits. So in our project we are using two of the most popular classifiers: support vector machines and k nearest neighbors. Support vector machines. Support vector machines are a way of are supervised learning algorithms, and they are binary classifiers, which means that they generally tend to classify elements into either class A or class B, which is two class. But we can solve the multi-class problem, that is the one we are facing right now with 26 classes, by using two different approaches known as one versus one and one versus all. Uh, for, for, for our project, we have chosen the one versus one approach. The one versus one approach states that whenever we have to, for every pair of classes present in our system, we need to generate a classifier, and the input image is tested across each of the classifier. The final output is determined based on the majority class of all each of these classifiers. So support vector machines work by mapping on the input image into a higher dimensional feature space, and they tend to distinguish the classes by separating them with hyperplanes, and they try to optimize the distance between the closest points in each of the class. So another popular classifier is the k nearest neighbor classifier, and k nearest neighbor classifier is a classifier which assigns a class to a given input image by observing k closest neighbors to it. The value of k is in our control. In our project, we have chosen the value of k is equal to 1, and uh, the winner for the output class is determined by the majority of all of its k neighbors. Uh, Here, to measure the distance or the similarity, there are three different metrics which we are using. Most popular ones are, the ones which are using right now are Euclidean distance, Manhattan distance, and Minkowski distance. Euclidean distance. These are the formulas. Euclidean distance. Uh, and moving on to the results. Uh, so based on the features mentioned here, I have performed few experiments on a sample image, and I calculated the accuracy for each of the uh, selected features. The accuracy here is defined as number of matching or number of correctly detected characters. So here you can see that this table represents the accuracies for the type text, and this table represents the accuracies for handwritten text. Here you can see that the grid vector tends to perform well in both the cases, and uh, here in this graph we can also see that the grid size. So this is a graph which plots between grid size and accuracy. So we can see that when the grid size is too low, the accuracy is very close to 0, and when the grid size is too high, the accuracy is very close to 0. But somewhere near grid size of 7, the accuracy tends to reach towards 1. And we have noticed the same for SVM classifier, and I uh, it would be safe to conclude that for somewhere around grid value of 7, we get an optimal feature set for any of the classifier. So here I would like to conclude my theoretical presentation here by saying that we have we are now able to detect the text from images. And uh, here the key takeaway is the grid vector seems to be one of the very good feature for providing high accuracies, and uh, the detection accuracy for handwritten text is lower than the typed text, which is expected because of the variation present in the handwritten text. Uh, Now we can move on to the demonstration part of it. For the demonstration part of it, I would like to uh, uh, I would like to walk you through the code once before actually running the demo. So here in this code, we can see that the all combined.py, this file is the major file, which is kind of the main application file for this application. And here, if you see, we first binarize the image. I mean, this includes pre-processing, applying the adaptive thresholding, and we get the final I mean the completely pre-processed image, which is ready for running the classification on. Once we have the image ready, we get the classifiers from a particular path. So we have already pre-trained these classifiers, and we have we can use this pre-trained classifiers. Now once we have the classifiers, so here you can see that we have a text detection module. So once the text detection module, we send the image as one of the parameter, try to get the text or word rectangle array out of it. These rectangle arrays are the bounding boxes, and we once we have the bounding rectangles, the first level of bounding word rectangle array represents the words in the image, and the second level of rectangle array represents the characters in each of the word. So once we have the character box here, we standardize it, and we send that character box into we send that character box to get the feature vector out of it. Once we have the feature vector, uh, we we use that feature vectors to and currently have both the classifiers KNN and SVM, and we predict based on the feature vectors, and we try to see what is the we try to see what is the predicted text. We since we know the input out of it, we can guess. I mean, we can see the accuracies of each of the predictions, and try to improve the system. If we go to the binarized module to it, so this is the one which does the pre-processing. You can see we are applying Gaussian blur and median blur, and adaptive thresholding to it. Once we have the image, we move on to the text detection module. So once we have the text detection module here we have the class word rectangle, and in the get text method, so first we dilate the image, and once we have the directory, we use the MSER to create the bounding I mean we create the bounding rectangles. So once we have the bounding rectangles here, we again perform MSER to individually detect the characters within the first level of bounding rectangles, which represents the word. Once we have both words and characters ready, we return the word rectangle array, which will be sent for feature extraction phase. So let me run an example, so which we can see right now. So this is the input image which I'm sending, which has a message, test message. Now when we run this input image against the set of predefined computer generated models, we can see that first the image is shown here. uh, this is the raw image. Now this image has been thresholded and you can see the difference in the edges of each word, and this is the dilated image which detects the text blobs, and this is finally the image which has the bounding rectangles across the word and the character. And as you can see, the classifier has run and it has actually detected pretty accurately that the words are test and message. So let's run this against different word and we'll see how it goes on. So the input image is orange apple. So after thresholding, you can see the edges are a little bit blurred. So we have detected the word blobs. And now we have the word and character segmented. And you can see here, this also has worked pretty decently. The only difference here is the second word apple is pretty accurate. The first word orange, instead of orange, it was uh, crunch, which is a miss by two characters. And there are many cases where accuracies are low sometimes, but on a general basis we do have pretty high accuracies for computer generated models. So let's run this example for one more handwritten model. And as expected, handwritten model generally. So if we run this against the handwritten model for the raw image orange ball, it has applied adaptive thresholding. You can see the difference in the contrast, and there are a lot of noises which are detected in this one. You can see, since it's a handwritten image, there's a lot of noise which is detected, and since you can since it's noise, there is not much of information which can be extracted out of it. And even in the extracted information, the second word ball tends to be pretty accurate. The first word has uh, has not been that accurate, but it still tried with uh, the first and last character being correct. This was like four. This word was missed by four characters. So yeah, this is the OCR application using various classification techniques, and this kind of concludes my demo. Thank you.